Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO and OFDM wireless communication systems. So, in the previous modules we were looking at the bit error rate performance of a multi-antenna wireless communication system. That is, when we have a single antenna at the transmitter, that is, we have a transmitter with a single antenna and then we have a receiver with multiple antennas. This is our receiver, and we have the various channel coefficients that are given as H1, H2, so on up to HL. So, we are considering a scenario with L antennas and the channel coefficients are given by H1, H2 up to HL are these are the various channel coefficients, and we have seen that in this context the optimal combining weights to be used at the receiver given by the maximal ratio combiner. So, optimal receive strategy or the signal processing algorithm at the receiver is to use maximal ratio combining. So, optimal receive strategy in this scenario or optimal receive combining is the maximal ratio combiner. Further, we saw that the SNR after maximal ratio combining, that is, if we look at the SNR, if I denote this by the SNR after maximal ratio combining, this is SNR after MRC or maximal ratio combining. This is given as P over sigma square times norm of H bar square, which is equal to basically P over sigma square times magnitude of H1 square plus magnitude of H2 square plus magnitude of HL square. So, the SNR after maximal ratio combining in a system with a single transmit antenna and L receive antennas is given as P over sigma square times norm of H bar square, which is basically P over sigma square times magnitude H1 square plus magnitude H2 square plus so on until magnitude of HL square. And therefore, now what we are going to do is, now let us consider this system. In this system, what I am going to do is I am going to denote G equals norm of H bar square, which is basically magnitude of H1 square plus magnitude of H2 square plus until magnitude of HL square. Now, what we are going to do is we would like to analyze the bit error rate of this multiple antenna wireless communication system. So, what we would like to do is we would like to analyze the bit error rate of this multiple antenna bit error rate of this multiple antenna wireless system, and towards that end what we will do is we are going to assume that we have, that is, we are denoting G equals magnitude H1 square plus magnitude H2 square plus so on up to magnitude HL square. Further, we are going to assume that these channel coefficients H1, H2 up to HL are independent, identically distributed Rayleigh fading channel coefficients with average power as 1. So, what we are going to assume is that H1, H2, these are independent random variables and identically distributed. This is also termed as IID, the IID assumption. These are independent identically distributed Rayleigh fading channel coefficients identically distributed Rayleigh fading channel coefficients which average power unity. That is, if I look at any channel coefficient and I look at the average power expected value of magnitude Hi square, that is equal to 1. So, these H1, H2, HL, these channel coefficients are independent, identically distributed Rayleigh fading channel coefficients with average power unity. And in such a scenario, now since H1, H2, HL are random, therefore, G is also random in nature. So, G is also a random variable and G is given as the random variable G, which is equal to norm H bar square. This is given as a chi squared. This is given as a chi-square random variable denoted by chi-square with 2L degrees of freedom. This is the number of degrees of freedom. This is 2L degrees of freedom, where L is the number of antennas, remember. And the distribution, the probability density function of this random variable is given by f of G equals 1 over L minus 1 factorial G to the power of L minus 1 e to the power of minus G. So, this G, which is norm of H bar square, is a chi-square random variable with 2L degrees of freedom, where L is the number of receive antennas, and the probability density function is given as 1 over L minus 1 factorial G raised to the power of L minus 1 e to the power times e raised to or e to the power of minus G. This is the probability density function of this effective gain G, which is norm H square. And therefore, now the received, we can write the received SNR as the received SNR, that is our SNR after maximal ratio combining. Our SNR M is, well, this is, as we already seen, norm H bar square times P divided by sigma square, but norm H bar square equals G. So, this is G times P divided by sigma square, which is basically equal to G times SNR after maximal ratio combining. And from our previous bit error rate analysis, from the analysis that we have done previously for the bit error rate for BPSK modulated communication symbols, we have seen that the bit error rate is given as, from bit error rate from previous bit error rate analysis, we have seen that our bit error rate equals Q of square root of or SNR at the receiver, which in this case is the SNR after maximal ratio combining, which is equal to Q of square root of G times SNR. So, this is our bit error rate, which is Q of square root of G times SNR is the bit error rate of this multiple antenna system, that is this wireless communication system with multiple receive antennas. And now what I am going to do is I am going to now, if you look at this expression q of square root of g times SNR, now you can see that this g is a random quantity. This is a random variable. So, we have to average with respect to the distribution of this random variable to get the average bit error rate. So, I have to average this expression average with respect to g to derive the average bit error rate of our multi antenna system. Of our multiple antenna system. And now this average bit error rate can therefore be obtained as, therefore the average bit error rate can be obtained as integral 0 to infinity q of square root of g times SNR times the distribution of g, that is f of g. So, to get derive the average bit error rate, what we are looking at is we are looking at the bit error rate q of square root of g times SNR, and we are averaging this with respect to the probability density function of the gain g, which is equal to norm of h bar square. And now I can substitute the expression for this, which is q of square root of g times SNR times g to the power of L minus 1 e to the power of minus g by L minus 1 factorial times d of g, and this is the integral that has to be evaluated, which I am not going to simplify over here, but I am going to write down the solution to this evaluation directly. And this integral can be simplified as, this can be simplified as equal to 1 minus lambda by 2 raised to the power of L summation small l equal to 0 to L minus 1 L plus L minus 1 choose L 1 plus lambda by 2 raised to the power of small l, where this quantity lambda is equal to square root of SNR divided by 2 plus SNR. So, what we are saying is, if we average this expression q of square root of g times SNR with respect to the probability density function of this gain g, which is norm of h bar square, we derive the expression, the following expression, which is written below in terms of lambda, and lambda itself is defined as SNR divided by square root of SNR divided by 2 plus SNR. Let me write this expression again here clearly. So, the average bit error rate equals 1 minus lambda over 2 raised to the power of L times small l equals 0 to L minus 1 L plus L minus 1 choose L 1 plus lambda by 2 raised to the power of L, where lambda is defined as follows, where lambda equals square root of SNR over 2 plus SNR. And you can see this notation, that is L plus L minus 1 choose L, that is N choose K or NCK notation, that is N choose K is equal to simply N factorial divided by K factorial times N minus K factorial, that is NCK or N choose K is N factorial divided by K factorial times N minus K factorial. And therefore, this is the expression for the average bit error rate of a multiple antenna system, of a this is the average bit error rate expression for a multiple antenna system. And it is important that you understand this, because we are going to use this expression fairly frequently in our analysis of wireless communication systems. For instance, let us simplify this for L is equal to 2, for L is equal to 2, that is a 2 antenna system. We have the bit error rate equals 1 minus lambda by 2 raised to the power of 2, small l equals 0 to L minus 1, L equals 2 to 2 minus 1 equals 1, L plus 1 choose L, 1 plus lambda over 2 raised to the power of small l, which is basically equal to 1 minus lambda by 2 whole square times, when L equals 0, this is 1 choose 0 times 1 plus lambda by 2 raised to the power of 0, plus when small l is equal to 1, this is 2 choose 1, 1 plus lambda by 2 raised to the power of small l is equal to 1. Now, let us look at 1 choose 0, that is equal to 1 factorial divided by 0 factorial times 1 factorial, again 0 factorial is 1. So, this is 1. 2 choose 1 is 2 factorial divided by 1 factorial times 1 factorial. So, this is equal to 2. So, the net expression is obtained as 1 minus lambda over 2 whole square times 1 plus 2 times 1 plus lambda divided by 2, and this is can be simplified as 1 minus lambda whole square times 1 plus lambda, that is 2 plus lambda. So, what we have derived is, we have derived the average bit error rate for a wireless communication system with L equals 2 antennas. So, this is the average bit error rate this is the average bit error rate with L is equal to 2 antennas, that is 1 minus lambda by 2 whole square times 2 plus lambda, and lambda, the quantity as we have seen already seen previously, lambda equals square root of SNR divided by 2 plus SNR. So, this is the average bit error rate for a system with L equals 2 antennas. And to understand this better, let us now do the following example. To understand this better, let us do a simple example. That is, considering a bit error rate, that is, what is bit error rate of a system with L equals 2 antennas at SNR dB, the dB SNR equals 20 dB. That is the question that we are asking is what is the bit error rate in this wireless communication system which has L equal to 2 antennas when the dB SNR equals 20 dB. Now, the first thing that we have to do is first we have to convert this dB SNR into normal SNR. So, we have SNR dB equals 10 log 10 times the actual SNR, which is given as 20, which implies our SNR equals 10 to the power of 2, which is equal to 100. Now, let us find the value of lambda. Lambda equals square root of SNR divided by 2 plus SNR equals square root of 100 divided by 102, and this is equal to 0.9901. So, we have calculated the value of lambda and we have found that the value of lambda for this scenario with 20 dB SNR and L equals 2 is 0.9901. Now, we will use the expression that we have derived previously for L equal to 2 antennas to find the average bit error rate, and the average bit error rate with L equals 2 antennas this is given as, remember this is given as 1 minus lambda whole square divided by 2 times 2 plus lambda, and substituting lambda equals lambda equals 0.9901 as we have derived just now. We get average bit error rate (7.2564) into 10 to the power of minus 5. So, what we obtain is that the average bit error rate at 20 dB in this wireless communication system with L equal to 2 antennas is 7.25 into 10 to the power of minus 5. So, the average bit error rate has been calculated as 7.25 into 10 to the power of minus 5. So, this is a simple example which illustrates how we calculate the bit error rate of a multiple antenna wireless communication system. And this can again be extended, since the formula that we have derived is for a general L, that is for which can be used for any number of antennas L. These results, that similar examples, that similar calculations can be done for wireless communication systems with any given number of antennas at any particular given SNR. So, these kind of simple so these examples can be readily extended to cases where we have a different number of antennas L and also a different SNR, and the procedure is the same. So, in this module what we have illustrated is we have illustrated how to compute the bit error rate of a multi antenna wireless communication system, and we are going to use see other applications of this in the subsequent modules. Thank you very much.